Hey guys, welcome to our first set of notes for chapter 17. I know this says chapter 18, but in your book, this is chapter 17. This is from, I think, perhaps an older edition. And it's going to be entropy, free energy, and equilibrium. A little bit of this should be repetition from Gen Chem, so I'm hoping that that'll be a nice reminder. So let's jump right into it. Okay, spontaneous reaction in chemistry. Spontaneous really just means that it's proceeding on its own accord. It doesn't necessarily mean fast or anything like that or unpredictable. It just means that it's spontaneous. It will naturally occur because it's favorable to do this. Water runs downhill. Sugar dissolves in a cup of coffee. Um, Water freezes below zero and ice melts above zero. That's just more favorable for them to do that. Heat flows from a hotter object to a colder object. A gas expands. And iron, when it's exposed to oxygen and water, will form rust. These are all spontaneous. They will proceed on their own accord. We don't have to do anything to them. So, spontaneous, more energy, more energetically favorable, so less energy. He proceeds that way. Not spontaneous would be the reverse of any of these reactions. And of course, this guy trying to ski up the hill would take a lot of energy. It would not proceed on its own accord. He would have to make that happen. And so that's not spontaneous. And so here you have gas in this bulb with a stopper and no gas in this bulb. You open the stopper, the gas diffuses through. That's spontaneous. Those gas molecules want to do that. Here you have gas molecules evenly distributed. Can we get them all to one side? Not really. That's not going to be very favorable. That's not going to be spontaneous. They won't spontaneously get 100% of the gas on one side of that valve. That's just not going to happen. So, spontaneous and non-spontaneous. So does a decrease in enthalpy mean a reaction proceeds spontaneously? Because you'll recall that a negative delta H was exothermic. So if something's exothermic, does that mean it'll happen on its own accord? Well, spontaneous reactions, here we have methane and oxygen forming carbon dioxide and water. Its delta H is very negative. It's almost negative 900 kilojoules. It's very negative. Is it spontaneous? Probably not. If I leave methane and oxygen, will it just burn? No, of course not. It takes something to get that started. Hydrogen and hydroxide ions forming water also has a negative delta H. And water, solid becoming liquid water, has a positive delta H. But of course, if it's above 0 degrees, this is a spontaneous reaction. But its delta H is positive. So enthalpy tells us a lot about heat exchange, which is good. Exothermic, endothermic, and the like. But it doesn't tell us if something's spontaneous or not. For that, we need to consider something different. So let's take a look at entropy, because entropy is what's going to tell if something is spontaneous or not. So entropy is S, or delta S for the change in entropy, is a measure of the randomness or disorder of a system. So if you have more order, you have a lower delta S, okay? If you have a lot of disorder in the system, you have a very high entropy, or S. And so we say that delta S is the entropy final minus the entropy initial, which is a formula you've seen a lot for temperature and all sorts of things like that. So the change from initial to final results in an increase in randomness. So SF is greater than SI. Then, of course, delta S is greater than 0. For any substance, the solid state is more ordered than the liquid state, and the liquid state is more ordered than the gaseous state. Hopefully that makes a lot of sense, because we've talked about solids and liquids and gases and how much freedom their individual molecules might have. And the more disorderly you are, like a gas, for example, would have a lot higher S than a solid would, because a solid is very ordered. And so the solid is less disorderly than the liquid, which is less disorderly than the gas, which is the most disorderly. So if you go from a solid to a liquid, delta S would of course be greater than 0, because we are increasing the disorder of the system. So one of the ways to think about this is to use microstates. Microstates is this distribution of particles in these areas. And basically the idea is that if all the particles are right here, then W would equal 1. All the microstates are present in one area. So we get this formula where if we distribute them out over 4 areas, we could put 4 here, 2 here, 1 here, 3 here. Or if we get 6 areas, we can organize them really any way we want. And so the more microstates you have, the more disorderly you can be. And so we get this law, which is S is equal to K, a constant, times the natural log of W, which is the number of microstates. And so we already know that delta S is equal to S final minus S initial. So we can plug that in to this former equation and get microstates final minus microstates initial. And then we get if the final microstates are greater than the initial microstates, then our delta S is probably positive because we become more disorderly, and vice versa. So that's one way to think about distribution of atoms in space. So here we have processes that lead to an increase in the entropy, so more disorderly. Solid going to a liquid, higher S, more disorder. Liquid to a vapor, more disorder. Solvent and a solute, more disorder. We had a nice organized cube of salt or sugar, and now those little salt and sugar ions are everywhere, and we have made them very disorderly. System at temperature 2, then we add heat to it, we become more disorderly. Atoms are moving much quicker, and they're all over the place, and it's more disorderly. So how would the entropy change? What if we condense water vapor? What do you think? What would that do? Condensing water vapor, increase entropy or decrease entropy? Okay, it would decrease entropy because we went from the vapor stage to the liquid stage. So the entropy decreases and the randomness decreases. Forming sugar crystals from a supersaturated solution. So we had them suspended in solution, now we get them to the crystal form. So we would be making them a lot more orderly. So again, our randomness decreases and our entropy decreases. Heating gas. Okay, well we just mentioned on the last slide that if something gets hotter, it gets more disorderly. So we'd have to say it increases. Subliming dry ice. So we went solid to gas, definitely increasing. And here are state functions, which is actually, we've seen something very, very similar to this earlier in the year. Entropy is a state function, and those are properties that are determined by the state of the system, regardless of how it was achieved. So 2 guys started at the bottom of the mountain, they made it to the top. That's all that matters. It doesn't matter that one went straight up and one took this really long roundabout way. They both made it to the top, and that's all that matters. And so the potential energy of hiker 1 and hiker 2 is the same, even though they took different paths. Entropy is the same way. If you have to break a reaction into different steps, that's fine. If you take the entropy change of individual steps, you get the entropy change of the whole reaction. It's kind of like Hess's law. So entropy is part of that. So let's go to the first law of thermodynamics. Hopefully this is something you remember. Energy can be converted from one form to another, but energy cannot be created or destroyed. The second law of thermodynamics is for this chapter. The entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. And so if a spontaneous process is occurring on its own accord in chemistry, that's what we say it does, then we are increasing the disorder of the universe. Every reaction that occurs makes the universe a little less orderly. That's the second law of thermodynamics. So the way we could word that with what we've learned is we are always increasing the entropy of the system or of the universe because things are getting more disorderly. And so here we have the S of the universe is the system plus the surroundings, and if those are greater than 0, then we're always increasing the disorder of the universe. So we're getting more and more disorderly. Kind of funny to think about. Now in an equilibrium process, we have the 2 arrows back and forth between products and reactants, and so there, if the system and surroundings is equal to 0, then our delta S would also be 0. So we can either stay where we are, or we can get more disorderly, and that's kind of where we have for entropy. So the standard entropy of a reaction is the entropy change for a reaction carried out at your standard lab temperature, 25 Celsius, and 1 atmosphere of pressure. And here's how you do this. You say the delta S of the reaction is equal to the products minus the reactants. And so what this would be is the coefficient of your products. You need to multiply it by. Another way you could write it, hopefully I don't mess this up too much, would be, pardon my sloppy Greek, this symbol, N for the number of moles, all the delta S's of our products, minus, same symbol, the sum of all the molar equivalents of all of our delta S's of our reactants. And so the N is the number of moles, and the delta S is something that you're going to get from your textbook. And so you say, okay, I have this many moles of the delta S value for C plus this many moles of the delta S value for D, and I put all that in brackets. So it's the sum of all of those minus the sum of the moles times the delta S of all my reactants. Little a is the number of moles, big A is the value for delta S that I'm looking for. So you add those up and you figure out if delta S is negative or positive. So, oh no, I wrote that nice little sloppy text in there, and then here's theirs, which looks great, way nicer than mine. So delta S of the reaction is the sum of the N S naught products minus the sum of N S naught reactants. So here's an example. What's the standard entropy change for the following reaction at 25 Celsius? So you go in your book and you find that big table. It's Appendix 3 towards the back. It's enthalpy, entropy, Gibbs free energy, that kind of stuff. And you look up carbon dioxide and you say, okay, carbon monoxide is worth this, oxygen's worth this, carbon dioxide is worth this. You find those values in your book and you set it up and you say, I have 2 carbon dioxides. So I plug in this value here, 2 times 213.6 minus, and then we're going to put all this in brackets, 2 times carbon monoxide's value, 197.9, because there's 2 carbon monoxides. There's only 1 oxygen, so plus 1 of the oxygen, 205.0. And then that's a done deal. You find out it's negative 173.6. So what does that tell us? You say, okay, well, that's negative. So if delta S is negative, I'm becoming less disorderly. It's a weird jump to make. I'm becoming more orderly if my delta S is becoming smaller. It's negative. And you say, well, geez, does that make sense? Let's look at this. 2 moles of gas, 3 moles of gas in the reactants goes to 2 moles of gas. So if I have 3 moles of gas becoming 2 moles of gas, am I becoming more orderly? Yes. And does my value reflect that? Yes. Math checks out. Conceptual entropy definition checks out. We probably did it right. So, what about changes in the system? If gases are produced or consumed, if a reaction produces more gas than it consumes, then our delta S is increasing. We have a positive delta S. If the total number of gas molecules diminishes, we're becoming more orderly. We have a negative delta S. If there's no net change in the total number of gas molecules, then S might be positive, might be negative, but it's probably going to be a small number because we're not significantly affecting the order of the system for better or for worse. So it asks us, what's the sign of the entropy change for the following reaction? So if you didn't have your table and you just had to use your brain and what you know about the world to figure this out, you'd say, okay, solid, very organized, 1 mole of gas goes to solid, no moles of gas. So I consumed gas to make solid. So I became more orderly. So if I became more orderly, my sign should probably be negative. And as the total number of molecules goes down, the delta S becomes negative. So not only do we understand this from a simple math, we can subtract point of view, but we should kind of understand this from the organized, how random and disorderly a system is. So entropy changes in the surroundings. We can always separate something into the system and the surroundings. You got your flask here, that's the system. You've got the entire atmosphere and world around it, that's the surroundings. In an exothermic process, if we release heat, we increase the entropy. So the delta S of the surroundings is increasing. If we add heat to the system, then the delta S of the surroundings is decreasing because it's losing heat. For the third law of thermodynamics, we have this cool idea that the entropy of a perfect crystalline substance is zero at the absolute zero of temperature. So if we can get something to 0 Kelvin, which we really can't, but if we could, the entropy would be zero. It'd be perfectly ordered, and that gives us the ability to get an absolute entropy starting with 0 Kelvin. We can figure out how entropy changes as we melt something, how entropy changes as we heat a liquid, and how entropy changes as we have a hot gas. So having that set 0 point for Kelvin gives us the starting point for building the standard entropy values that we have today. So we use this using that same law we learned earlier, which was S, the entropy is equal towards K, the constant natural log of the microstates. And the microstates would equal 1, and S would equal 0 if we could be at absolute 0. And so it gives us a starting point. So we will leave off there for right now. That's plenty to get you started. We'll come back to Gibbs free energy next time. So thank you.